Okay, let's investigate the concept of work. We're going to cover the work done by a constant force and a varying force. Specifically, we'll deal with forces dependent on the position. So the work is defined as follows. We'll use the letter W for work, which is not to be confused with the weight. We use the same symbol. And this is equal to the sum of all the forces dot dr between R1 and R2. Let's look at each term. dr is our regular position vector, which is for cases where we have a path. Therefore, we can represent every point on that path by a vector r, which can be decomposed at any time as x and y. So dr will become x di plus y dj in 2 dimensions. Sum of the forces is our usual left-hand side of Newton's second law, which represents the sum of all the external forces acting on the system, and we have a dot product. So it means that every time we are going to have external forces acting on an object, and those forces will tend to move our system from one position R1 to another position of R2. The work done is going to be the projection of all those forces aligned along the direction dr. So the further you go, the more work you're going to be doing. The higher the force, the higher the work you're going to be doing, or the more work you have to put into the system in order to displace it from position R1 to position R2. Now remember, if this is a dot product on the right hand side, this must be a scalar. So work is a scalar, work is just a number. Okay, let's look at the units. R as the units of meter, because it's a displacement. F as the units of Newton, which remember is equivalent to kilogram meter per second squared. Therefore, if the right hand side is the product of kilogram meters per second squared and meters, the left hand side must be having the same units as the right hand side, which must be kilogram meter second squared times meter again. Therefore, kilogram meter squared per second squared. And this is defined as joules. So we have to be careful with those units. They look pretty much the same. Remember that Newton is kilogram meter per second squared. Joule is Newton meter, or kilogram meter square per second squared. So joule can usually be written either as kilogram meter squared per second squared or Newton meter. There are the two standard ways to express the units of work. Now remember, if you want to use joule, you need to make sure that all your forces are in Newton and all your distances are in meter. So since the work is a dot product, it will follow the same properties of a dot product. So let's summarize them here. If you have two vectors, A and B, whose angle between the vectors is theta, then remember that A dot B is a scalar, which can take a whole range of values. Let's imagine that A is perpendicular to B, and in this case the angle between the two vectors is 90 degrees. Therefore, the magnitude of A dot B is AB cosine 90, which will give us 0. So remember that when two vectors are perpendicular to another, the dot product will give us 0. In your case, if the sum of all the forces is perpendicular to the displacement, then the work would be equal to 0. Other extreme case, if A is parallel to B and in the same direction, then A dot B will be A dot times B magnitude times cosine of 0, and cosine of 0 is 1, therefore the dot product will take its maximum value, which will be the case for us if the sum of all the forces are in the same direction as the displacement. Then the work is going to be just sum of the forces dr, all scalar notation. And last case, remember, if A is parallel to B but in its opposite direction, then A dot B is magnitude of A times magnitude of B times cosine of 180, which is minus 1. Therefore the dot product will take its maximum value, but on the opposite side of the spectrum, negative value. Therefore in this case the work will be negative. So in this case, if we have a displacement dr in this direction, but the sum of the forces is in the opposite direction, then the work done is going to be minus dr. So, example, if you have an object sitting on a surface and you're pushing this object with a force F, and you're being told that this object is going to move along the inclined plane. Obviously, if the direction of F is towards the right, its acceleration is going to be towards the right as well. Therefore, dr is also towards the right. Since vector F is also towards the right, the work done by F on the system will be, if this is position R1 and we're going to move this object all the way up to position R2, in this case the sum of the forces reduces to my force F, which I need to take the dot product with dr. Now since F is in exactly the same direction and parallel to dr, then the dot product will give us automatically the product of each of their magnitude. Therefore the work will become R1, R2 magnitude of F times dr. If F is given to us as 10 Newton, it's a constant. Therefore we have 10 dr. We can take 10 out of the integral, R1, R2, and we end up with work is equal to 10 times the change of position, R2 minus R1. Therefore if we move by, say, 5 meters, then the work will be 10 times 5 is equal to 50 joules. Similarly, let's imagine that now we're going to have the same situation, except we push with a force having a particular angle, say alpha. Let's imagine we know our force, it's a constant 10 Newton, and this subject will go from position R1 all the way up to position R2, which end up being, say, 5 meters again. The work done will be R1, R2. The only force present in this particular case that we will consider, or specifically the work done by the force F, will be our force F dot dr. So the first thing we want to do is identify the direction of our displacement. Our displacement is along the plane. This is our dr. And we want to take the dot product between F and dr. Therefore we need the angle between F and dr. Now remember, we can take that vector F and move it all the way up to here from the same point. Then we recognize that this is going to be our angle alpha. Therefore F dot r is only going to be considering the component of F which is parallel to dr. In our case, this will be R1, R2, f sine alpha dr. If we're moving from 0 to 5 meters, f sine alpha dr. Again, f sine alpha is a constant, we can take it out, and therefore we just need to multiply f sine alpha by 5 minus 0, which is 5. If f is 10 and let's say alpha is 30, then the work done is 10 sine 30 times 5. Now last case, if for example we still have f pushing in this direction, but there's going to be some friction. Again, we're going to go from R1 to R2, so our dr is going towards the right, but friction is going to go opposite to the direction of motion. Therefore, we know that the frictional force is going towards the left. Let's imagine we know the magnitude of the friction, which is 1 Newton, and we're concerned about the work done by this particular force only. Then the definition tells us that we need to replace sum of the forces by just f dot dr. Now in this case, f is parallel to dr, but in the opposite direction. Therefore, we know that f dot dr will give us f times dr times cosine of 180, which is nothing else than minus 1. Therefore, the work is negative. Again, if f is given as 1 Newton, it is a constant, we can take it out. And our dr is nothing else than, say, 5 meters, 0 meters. Which is 5 minus 0, which is 5. And if f is 1, then the work done is minus 5 joules. So those are 3 common examples that we will see. So another way of looking at the work, especially if you have, say, several forces. Let's take the case where now we're going to consider the total work of an object being, say, pulled by a force T of 10 Newton with an angle of 30 degrees, and then we're going to have the weight applying to this object. We're going to have the normal force, and we're going to have some friction. So we've done a full free body diagram on this system, and we would like to know the total work that is needed to apply to our system to move it from position 1 to position 2, say towards the right, which is 5 meters away. So the work done will be the sum of all the forces times dr. So for us to be able to calculate the total work, since we know the sum of all the forces, it implies that we need a free body diagram. So we're going to pick our axis such that dr is going to be a line, say, along our x. Then really the total work is nothing else than x1, x2, sum of the forces dot dx, because we're going in the x direction. So sum of the forces, we have 1, 2, 3, 4 forces. Therefore, the work total is F plus N plus T plus W dot dx. Okay, let's express each of those vectors in component notation. So I'm going to go very slowly. Later on you can skip this, steps as you see it right away. F will be minus f I, because f is going towards the left. N is nj. T is going to have two components. T cosine theta in the I direction, and T sine theta in the j direction. And then we're going to have W, which is minus mg j. This is the sum of all the forces in component addition, to which we will dot it with, I'm going to rewrite dx x vector as dx times I. So now it's easy to take the dot product. We know that all the terms that will survive are the terms which are in terms of I, because dx is along the x and therefore is dx times I. The first term will survive. We will get r1, r2 minus f. N will not survive because j dot I will give us 0. The third term will, however, survive, t cosine theta. This one will not, and this one will not. And now we have a scalar version of the work, which we can do easily. If we're given, say, f 1 Newton, t 2 Newton, theta 30 degree, all those values are constant. Therefore, we can take them out of the integral, and we have minus f plus t cosine theta. I'm sorry, if we're replacing x, then this becomes x's, x1, x2 dx. This is nothing else but 5. So the total work is minus 1 plus 2 cosine 30 times 5. So let's go back to the general case. We have seen with all those examples that if we have the work, which is R1, R2, sum of the forces that they are, all we need to do is first analyze all the sum of the forces. Therefore, this implies that we do a free body diagram. Once we have this, you want to make sure that you pick one of your coordinate system, x and y, such that one of those two is aligned with your dr. That will make your life easier. So if you being told that you're moving in the x direction, then you want to replace the work as dx. If you're being told that you move up and down in the y direction, then really this become dy. So be clever and align your dr in the same direction as the motion of this particular object. And then we have seen that most of the forces so far were constant. If you're dealing with a weight, with mg. If you're dealing with a normal force is also going to be a constant. Frictional force is going to be a constant. So if they're all constant, once you have taken the dot product and figure out the direction and the minus sign and the angles, etc., 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 really you can take them out of the integral. So for constant forces, this definition of work can be reduced as sum of the forces R1, R2, dr. Therefore, sum of the forces, and this is nothing else than dr. So for constant forces, you can just take the sum of the forces, add them up, identify your dr, which is the change of position, and then take the dot product between every one of your forces along that particular direction r. So again, if you're moving in the x direction, this will become sum of the forces in the x, that's all you need, times delta x. If you're moving in the y direction, then this can be rewritten as sum of the forces in the y direction times dy, after you've taken, of course, the dot product. Which means that you can rewrite this as really you want the sum of the forces parallel to your displacement. So you might see that notation. And if you write it that way, then you can skip the vector notation. So as you have a sum of the forces to consider, you only want to consider the component of your forces which are parallel to your displacement. Example, W is here, N is here, let's say T is here, F is here, and another F is here, and you're being told that you move this object from this position to this position. And the first thing that you want to do is identify dr, and you've realized that dr is in this direction. Let's align it with our x component system. So this would be dx, dy, or y and x. So this is my x axis, this is my dx, and this is my y axis. So you know that your displacement is in the x direction, which is this one. So all you want is the component of all your forces in the x direction only. N will not show up because since n is perpendicular, W will not show up. F will show up entirely, the whole magnitude of F, but with a negative sign because it's pointed opposite to the displacement dx. Big F will be present also, and this time positive because it's pointing in the same direction as your positive x. And T will also be present. Say if you know this angle alpha, it will be T sine alpha, which represent the x component of your T. You just take this and you multiply by your dx or delta x, and this should give you the work done by all the forces acting on your system. So when forces are constant, it's quite easy. If the forces that you're dealing with are not constant, but are a function of displacement, then the only difference is as you calculate the work, you cannot take the force out of the integral anymore. But that's okay, as long as you're being told the functional form of that force, then you just leave it into the integral, integrate it, prime done. So if you're being told that, say, the forces acting on your system is just one particular force, and this particular force is defined as kx, with k being constant, say 1, 2, 3, and x represent the displacement. And let's imagine that you're trying to move your object, which is subjected to this force, in the x direction. So you're moving this object with the force F in this direction, which we will pick to be our x. So in this case, the work done becomes x1, x2. I'm going to put the functional form of my force here, delta x times dx. Since F is going in the same direction as my dr, then the dot product will just give me the product of vector kx and vector dx. So once I got to this point, well, it's very easy. I just need to integrate. K is a constant, I can take it out, and I just need to integrate x dx, and that's pretty trivial. This will becomes x2 over 2. Therefore the answer would be k over 2 x2 squared minus x1 squared. So the only difference between a varying force as a function of position and a constant force is that the varying force will need to be kept inside the integral. You cannot just take it out of the integral and multiply it by the displacement directly. You have to leave it in there, integrate it as a regular function. Now graphically, if you're plotting r versus f, and let's say your force is constant, so the force remains the same as you displace your object, then obviously the magnitude of the force doesn't change, and you would expect this to happen. If you apply that force, which is constant, let's say 10 Newton, and you move the object between position 0, or r1 is equal to 0, to say r1 is equal to 5 meter, then the work done is going to be nothing else than the area under the curve. So graphically, the work done is nothing else than the area under the curve created by your force F and your displacement axis. If now your force depends on the position, let's look at this example again, where F is equal to kx, then obviously if say k is equal to 2, f is going to be equal to 2x. Therefore, we're going to have a straight line of slope is equal to 2. We apply this force, which seems to increase as we increase our position, and we go from position 1 to position 2, which is say again from 0 to 5. Then the work done will be again the area under the curve. If you pick any force which has a weird function of r, say like this, no problem. All you do is identify your initial position, identify your final position, calculate the area under the curve, which is nothing else than what we've been doing here, and you will get the work done by this force